Welcome to EMS 220. In this video, we will examine the graphical features of EFTC Explorer that support modeling of temperature in a water body. There are 5 components of the graphical interface: surface heat exchange, initial conditions, boundary conditions, ice options, and general settings. Let's go. To set up a temperature simulation in EFTC Explorer, we must first activate the temperature module. Right-click on the modules tree to activate the temperature module. In order to set up the temperature module, the user should right-click to open the temperature parameters dialog. 5 tabs are present in the temperature parameters dialog: surface heat exchange, initial conditions, boundary conditions, ice, and general. The Surface Heat Exchange tab is where the user sets the surface heat exchange submodel. This drop-down list contains 6 options. Settings which are relevant to the surface heat exchange are provided in the surface heat transfer coefficient frame and in the light extinction coefficients frame, depending on which option is selected. The options for the surface heat exchange submodel are no atmospheric linkage, full heat balance legacy, external equilibrium temperature, constant equilibrium temperature coefficient, equilibrium temperature C=equal W2 method, and full heat balance with variable extinction coefficients. Constant and spatially or temporally variable heat transfer coefficients can be configured for both latent and sensible heat. Transfer coefficients can be configured to vary with wind speed, or can be spatially varied using the Apply Cell Properties via Polygon dialog. If heat transfer coefficients are set to vary with wind speed, then the value assigned will be considered the minimum or background value in the model. The Full Heat Balance with Variable Extinction Coefficient option provides the users with the option of allowing light extinction to be dependent on the total suspended solids in the water column, thereby making light extinction temporally and spatially varying. The extinction factors are determined on a cell-by-cell basis for each time step based on TSS, and if the water quality model is active, based on particulate organic matter, dissolved organic matter, and chlorophyll A as well. The Initial Conditions tab contains methods to assist the user in assigning initial conditions for temperature. The initial temperature can be set to a constant value or assigned to be spatially varying. To set either of these options, select the Assign button. As with salinity, the user can set a constant value in the constant field under the Values to Set frame. The user can set this constant to certain layers in the Layer Options frame and then select Assign. If the values to be set vary spatially, the initial temperature can be based on XYZ or vertical profile data. The user should then browse with the Add File button in the Data Files frame to add these datasets. Various interpolation options are provided in the Interpolation Options frame, including replacement of existing data and using the maximum or minimum values. Selecting the More button provides further interpolation options, including order of inverse distance weighting interpolation, number of neighboring points, and number of quadrants. Both constant and spatially varying initial conditions can be defined in the Initial Conditions for Bed Temperature frame. If only Allow Spatially Variable Bed Temperatures is checked, the user will be able to use the text boxes below to set a spatially constant initial condition. During the course of the simulation, the temperature will be allowed to vary based on the forcing functions and initial bed temperatures and thickness. If the Use Spatially Variable Bed Temperature and Thickness is checked, then the user can assign spatially variable bed temperatures and thicknesses using the Assign Cell Properties by Polygon dialog. Both the temperature and thermal thickness will be allowed to vary during the simulation. The Boundary Conditions tab for the Temperature Parameters form allows the users to configure the atmospheric data, water temperature data, and ice data options. EFDC Plus can include the effects of a horizontal pressure gradient in the model domain on the hydrodynamics. This allows EFDC Plus to address pressure variations in large coastal systems. The pressure solution of EFDC Plus can optionally include variations among multiple atmospheric stations in the model domain. The modified pressure solution does not make any contributions to the hydrodynamic field when the number of pressure series is less than 2, because the horizontal pressure gradient component of the atmospheric pressure is always 0. However, if the pressure gradient is not a constant in the computational domain, then gradients are computed, and these will impact the external solution pressure field. This approach does not violate the hydrostatic assumption. The user can select the Edit button to open each atmospheric series and edit them. As with wind data, the series weighting for multiple atmospheric series can be computed for the model domain with a quality index that indicates how the user rates each time series and time block within that series. As with salinity, temperature data time series must be associated with a boundary condition. This is done using the Boundary Condition Editor, which was discussed in the EEMS 120 video. A robust iced submodel is available in EEMS. The ice formation and melt are currently simulated by EFDC Plus using a coupled heat model and fully handled by EFDC Explorer. Ice options are available under the Ice Computational Options frame. For all these options, ice is only enabled if the user is simulating temperature. The user has 5 options for simulating ice: either disabled, using an external ice time series, a specified ice on or off time series, and a heat-coupled ice model, either with or without phrasal transport. Let's take a closer look at each of these options. The external ice time series option does not compute ice formation or melt, and it is not linked to the heat balance. This option simply requires the user to provide a fraction of ice coverage and ice thickness for every cell. The effect of this option is that the heat exchange at the air-water interface has no direct effect on ice melt. The Use Specified On-Off Ice Cover option is effectively a global toggle so that ice may be turned on or off over the whole domain. The time series file that populates this option lists a date and a toggle on-off within the input file istat.imp. The heat-coupled ice model applies mass conservation during ice growth and melt. Ice is always calculated in the heat-coupled ice model, similar to the C=W2 model. The ice cover model allows light to be attenuated through the ice. The solar radiation absorption is accounted for in this process. When calculating ice formation in a river, if the air temperature is less than freezing, generation of ice crystals takes place in the water. These crystals are called phrasal flakes. As the phrasal flakes are lighter than water, they float and form ice pans. As these ice pans grow, they eventually form ice floes. As the phrasal ice rises, it is necessary to input a rising velocity into EE to account for this. The General tab in the Temperature Parameters form allows the users to configure the bed heat exchange coefficient and evaporation options. The bed heat exchange coefficients must be provided in order to simulate heat transfer between the water column and bed. By default, these values are 0, so that heat transfer with the bed is not simulated by default. Loss of mass can be optionally included in the mass balance of the model domain using the evaporation options provided in the General tab. Note, however, that the latent heat flux is always considered in the surface heat balance regardless of the evaporation option selected here. Evaporation options will only appear for the following surface heat exchange options: full heat balance legacy, full heat balance with variable extinction coefficients, and equilibrium temperature, CEQUAL W2 method. Each of the options contained in the drop-down menu provide different options for parameterizing the mass loss due to evaporation. By default, EFDC Plus will ignore mass loss due to evaporation and rainfall. Alternatively, these values can be provided in the acer.imp file. A variety of different options are available for evaporative loss to be computed as well. Thank you for watching. You can find a link to the next video below.